Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. The solar system, with its planets, moons, asteroids, and comets, stretches far beyond the orbit of Neptune, into regions so remote and mysterious that they were unknown until the late 20th century. These outermost reaches hold secrets about the origins of the solar system, the nature of distant icy bodies, and even the potential for long-period comets that occasionally streak across our skies. Among the most fascinating of these distant realms are the Kuiper Belt and the Oort Cloud, often considered the outer edges of our solar system, forming a vast icy frontier that challenges our understanding of planetary science. The Kuiper Belt is a circumstellar disk, a vast ring of icy objects orbiting the Sun beyond Neptune, extending roughly from 30 to 50 astronomical units in AU from our star. While the inner solar system is dominated by rocky planets in the asteroid belt, the Kuiper Belt is composed primarily of small bodies made of frozen volatiles like methane, ammonia, and water. These icy remnants are considered leftover building blocks from the formation of the solar system, primordial material that never coalesced into a planet due to the gravitational influence of Neptune. Objects within the Kuiper Belt are diverse in size and composition, ranging from small comet-like bodies just a few kilometers across to dwarf planets such as Pluto, Haumea, and Makemake, each with unique characteristics and fascinating histories. Exploration of the Kuiper Belt has transformed our understanding of the solar system. Prior to the discovery of Pluto in 1930, scientists had no concept of this distant region. Over the decades, as telescopic technology improved, and astronomers began detecting more and more small, icy bodies beyond Neptune, leading to the realization that Pluto was not an isolated anomaly, but part of a vast population. Today, the Kuiper Belt is recognized as a dynamically rich region, home to thousands of known objects and potentially hundreds of thousands more, too faint or distant to detect. Its inhabitants are classified into several categories: classical Kuiper Belt objects, or cubewanos, which have nearly circular orbits relatively undisturbed by Neptune's gravity; resonant objects like Pluto, which are locked in orbital resonance with Neptune; and scattered disk objects, whose eccentric orbits take them far beyond the main belt, influenced by past gravitational interactions. The Kuiper Belt is not just a collection of frozen rocks, it is a window into the early solar system. These bodies preserve clues about the composition of the protoplanetary disk from which the planets formed, and their surfaces often bear the scars of cosmic impacts accumulated over billions of years. Spectroscopic studies reveal a mixture of ices, including water, methane, and ethane, while some exhibit coloration suggesting complex organic molecules processed by cosmic radiation. Observations of Kuiper Belt objects also hint at internal activity in some cases. For instance, Pluto's heart-shaped Tombaugh Regio and its icy plains suggest geologic processes reshaping its surface despite its distance from the Sun. Such findings challenge our notions of what is possible in the frigid outer solar system, hinting that even these distant worlds can harbor dynamic and evolving landscapes. Beyond the Kuiper Belt lies an even more enigmatic region, the Oort Cloud. Named after the Dutch astronomer John Oort, who hypothesized its existence in 1950, the Oort Cloud is a hypothetical spherical shell of icy bodies enveloping the solar system at distances ranging from roughly 2,000 to 100,000 astronomical units. Unlike the relatively flat and concentrated Kuiper Belt, the Oort Cloud forms a vast, diffuse sphere that may contain trillions of icy objects, making it the ultimate repository of cometary material. Its distant location means that objects within the Oort Cloud are only weakly bound to the Sun, easily perturbed by passing stars or the tidal influence of the Milky Way itself. These disturbances can send long-period comets hurtling inward toward the inner solar system, where they become visible as brilliant transient spectacles in the night sky. The origin of the Oort Cloud is a subject of ongoing study and debate. It is believed that the objects currently residing in this distant sphere were originally formed closer to the Sun in the planetary region of the early solar system and were subsequently ejected by gravitational interactions with the giant planets. This process scattered them outward over millions of years until they reached the outermost fringes, where they settled into the cloud's loosely bound orbits. Some theories suggest that a fraction of Oort Cloud objects may have been captured from other stars during the Sun's early years within its birth cluster, meaning that the Oort Cloud could contain material from beyond our own solar system. This idea paints a picture of the solar system's edge, not as an isolated boundary, but as a dynamic frontier shaped by both internal and external forces across cosmic time. While the Oort Cloud remains largely theoretical, its existence is inferred from the behavior of long-period comets. Unlike short-period comets, which originate in the Kuiper Belt or scattered disk and orbit the Sun in under 200 years, long-period comets have highly elongated orbits, some taking millions of years to complete a single revolution. Their trajectories are often random and isotropic, suggesting a spherical source like the Oort Cloud. Famous comets such as Hale-Bopp and Hyakutake are believed to have come from this distant reservoir, providing rare glimpses of material that has remained essentially unchanged since the formation of the solar system. Studying these comets offers a unique opportunity to analyze pristine cosmic ice and dust, revealing the chemical building blocks from which planets and ultimately life arose. The Kuiper Belt and Oort Cloud are not merely static collections of frozen bodies. They represent a dynamic interplay of gravitational forces, collisions, and cosmic evolution. Interactions between Kuiper Belt objects can generate debris that replenishes cometary populations, while perturbations from Neptune or passing stars can reshape orbits and trigger new activity. Occasionally, collisions in these distant regions produce fragments that migrate inward, potentially intersecting Earth's orbit. Such processes underscore the role of these remote regions, not only as a historical archive of the solar system's formation, but also as ongoing contributors to its current dynamism. In addition to their scientific significance, the Kuiper Belt and Oort Cloud also challenge the human imagination, stretching our conception of the solar system's scale. To reach the inner edge of the Kuiper Belt is already a journey of billions of kilometers, far beyond the realm of Mars or Jupiter. Beyond it, the Oort Cloud extends halfway to the nearest stars, occupying a volume of space so vast that it borders interstellar space itself. These distant regions remind us that the planets we see in the night sky are only a tiny fraction of what exists around the Sun. The solar system is not merely a compact assembly of planets and moons, but an immense and complex structure, with boundaries that blur into the depths of interstellar space. Exploration efforts have begun to probe these distant realms, though they remain largely out of reach for human spacecraft. NASA's New Horizons mission, launched in 2006, provided humanity with its first close-up look at a Kuiper Belt object when it flew past Pluto in 2015, revealing its complex geology, atmosphere, and moons. Continuing its journey into the Kuiper Belt, New Horizons later encountered Arrokoth, previously known as 2014 MU69, a small bilobed object that offered a direct glimpse of the primordial building blocks of planets. Such missions demonstrate that even at the edge of the solar system, human ingenuity can capture detailed data, opening windows onto worlds previously imagined only from afar. Despite these advances, the Oort Cloud remains largely unexplored, a theoretical construct inferred from indirect evidence. Its vast distance and low-density distribution of objects make direct observation extraordinarily difficult, requiring new technologies and innovative approaches to detect or study it. Some proposed methods include monitoring the infrared glow of distant icy bodies, studying perturbations in cometary orbits, or employing large-scale surveys capable of detecting faint, slow-moving objects at extreme distances. As technology advances, humanity may one day directly probe the outermost edges of the solar system, transforming speculation into observation and confirming the Oort Cloud as a tangible component of our cosmic neighborhood. The study of the Kuiper Belt and Oort Cloud also has implications for understanding planetary systems beyond our own. Observations of exoplanetary systems frequently reveal circumstellar disks of gas and dust, analogous in some ways to the Kuiper Belt, suggesting that the processes shaping our outer solar system may be common throughout the galaxy. By studying these distant regions, we gain insight into the universal mechanics of planet formation, migration, and the preservation of icy debris. Moreover, understanding how comets are scattered from distant reservoirs to interplanetary regions may illuminate the delivery of water and organic compounds to terrestrial worlds, a key factor in the emergence of habitable environments. The dynamic nature of these outer regions also highlights the interconnectedness of the solar system. While the Kuiper Belt lies relatively close, interacting with Neptune and contributing short-period comets, the Oort Cloud extends into interstellar space, its objects sensitive to the gravitational tug of nearby stars and galactic forces. This interplay underscores a delicate cosmic balance, in which events billions of kilometers away can influence the solar system's evolution and, occasionally, life on Earth. Each comet that graces our night sky is a messenger from these distant regions, a reminder that the solar system's edge is not merely a boundary, but a source of ongoing activity and discovery. The Kuiper Belt and Oort Cloud also challenge our classification of celestial objects. Pluto's reclassification as a dwarf planet in 2006 reflected its membership in the Kuiper Belt, along with hundreds of similar-sized bodies, reshaping the traditional notion of planets. Beyond classification, these regions prompt philosophical reflections on the nature of the solar system, how we define its boundaries, how we distinguish between planets, dwarf planets, and smaller bodies, and how we conceive of a system whose outermost reaches are barely tangible, yet vitally important in understanding cosmic history. At the heart of these explorations lies a profound narrative of time and persistence. The Kuiper Belt and Oort Cloud contain relics from the dawn of the solar system, objects that have endured for over 4 billion years, largely unchanged. They are archives of primordial matter, preserving chemical signatures, isotopic compositions, and structural features that reveal the conditions of the early protoplanetary disk. Studying these bodies allows scientists to reconstruct the solar system's formative processes, to understand the migration of giant planets, and to trace the origins of cometary material that occasionally reaches Earth, delivering water and organics that may have been crucial for the development of life. Even as we gaze upon these distant frontiers, the Kuiper Belt and Oort Cloud serve as a bridge between observation and imagination. They extend the solar system into realms beyond direct human experience, offering both scientific opportunity and a sense of cosmic wonder. Each discovery in these regions expands the boundaries of knowledge, revealing that the solar system is far more intricate, dynamic, and extensive than once thought. From the icy plains of Pluto to the faint comets arriving from the Oort Cloud, these distant bodies narrate a story of formation, evolution, and ongoing change that continues to unfold at the edges of our sun's domain. Delving deeper into the Kuiper Belt reveals a surprisingly diverse collection of worlds, each with its own story to tell. While Pluto often captures the spotlight, it is far from the only fascinating inhabitant. Haumea, a rapidly rotating elongated dwarf planet, spins so quickly that its shape is stretched into a flattened ellipsoid. Its fast rotation also contributes to the presence of a ring system, an unexpected feature for such a distant world. Makemake, another dwarf planet, showcases a bright surface rich in methane ice, hinting at chemical processes that may alter the outer layers of these icy bodies. These objects are far more than frozen rocks. They are dynamic systems with complex surfaces, moons, and even internal heat sources in some cases, reshaping our understanding of what is possible in the coldest reaches of the solar system. Beyond these dwarf planets, countless smaller Kuiper Belt objects populate the region, many of which remain undiscovered due to their small size and vast distance. These objects, often just tens of kilometers across, carry important scientific information about the solar system's formative era. Collisions between Kuiper Belt objects generate debris that can migrate inward as short-period comets, replenishing the population of icy visitors to the inner solar system. In this way, the Kuiper Belt serves as a reservoir, a cosmic freezer preserving primordial matter while slowly sending fragments toward the sun over millions of years. Observations of these small objects whether through direct imaging or stellar occultations, continue to reveal surprises, from binary systems where two bodies orbit one another to peculiar rotational patterns that challenge traditional models of collisional evolution. The dynamics of the Kuiper Belt are influenced heavily by Neptune, whose gravitational pull sculpts the orbits of many of its members. Resonant objects locked in orbital resonance with Neptune maintain stable orbits despite the planet's perturbations. For instance, Pluto is in a 3-to-2 resonance, completing 2 orbits around the Sun for every 3 orbits of Neptune. Such resonances act as protective mechanisms, preventing close encounters that could destabilize their trajectories. Meanwhile, scattered disk objects experience more chaotic interactions, sometimes being ejected into highly elongated orbits that extend hundreds of astronomical units from the Sun. These interactions underscore the Kuiper Belt as a dynamic region, not static but constantly evolving under the gravitational influence of giant planets and external forces. Moving outward, the hypothetical Oort Cloud presents an even more profound frontier. Its spherical shape contrasts sharply with the relatively flat plane of the Kuiper Belt, hinting at a different formation mechanism and dynamical history. Objects in the Oort Cloud are subject to weak gravitational binding by the Sun, making them sensitive to the slightest perturbations. Passing stars, molecular clouds, and even the galactic tide, caused by the Milky Way's gravitational field, can nudge these bodies onto paths that send them hurtling toward the inner solar system. This process explains the appearance of long-period comets, which arrive unpredictably from any direction, sometimes after millions of years in the distant reaches of the cloud. The Oort Cloud thus acts as a distant, icy gatekeeper, occasionally releasing comets that enrich our understanding of solar system chemistry and dynamics. One of the most intriguing aspects of the Oort Cloud is its potential to include interstellar material. During the Sun's early formation within a dense star cluster, interactions with neighboring stars could have transferred icy bodies from other systems into our own Oort Cloud. If true, this means that some long-period comets are not just ancient solar system relics, but visitors carrying material from beyond our star, offering a rare glimpse into the broader galactic environment. Studying these objects could provide valuable insight into the diversity of planetary systems and the processes that shape them, potentially revealing commonalities and differences in how star systems evolve across the Milky Way. Despite its distance, the Oort Cloud has tangible consequences for Earth and the inner planets. Each long-period comet that reaches the inner solar system carries information about conditions billions of kilometers away. Their nuclei, composed of pristine ices and dust, serve as time capsules from the early solar system, largely unchanged since formation. When comets such as Hale-Bopp or Hyakutake become visible, they are not only spectacular celestial events, but also scientific treasures. Studying their composition, dust tails, and gaseous emissions helps scientists understand the chemical building blocks available during the solar system's birth, shedding light on the processes that might have delivered water and organic molecules to Earth, influencing the origins of life. The interactions between the Kuiper Belt, scattered disk, and Oort Cloud highlight a continuum of icy bodies spanning vast distances. Objects can migrate from one region to another, influenced by planetary resonances, collisions, or external perturbations. This interconnectedness blurs the boundaries between these regions, suggesting a solar system that is more dynamic and integrated than the traditional model of isolated zones. The processes operating at these distant edges have repercussions that echo inward, reminding us that even the most remote objects are part of a larger gravitational ballet that shapes the solar system's architecture. Human exploration has begun to shed light on these distant worlds, though much remains speculative. NASA's New Horizons mission provided unprecedented insight into the Kuiper Belt, revealing not only Pluto's intricate geology, but also the characteristics of smaller objects like Aerokoth, which is thought to represent an unaltered primordial planetesimal. Such observations confirm that Kuiper Belt objects are remnants of the original protoplanetary disk, offering direct evidence of the building blocks that coalesce to form planets. As technology advances, future missions may venture even further, potentially probing the outer Kuiper Belt and scattered disk, or even attempting indirect detection of Oort Cloud objects through innovative observational techniques. The Kuiper Belt and Oort Cloud also illuminate broader questions about the solar system's formation and evolution. The distribution of icy bodies informs models of planetary migration, suggesting that the giant planets did not remain in their current positions, but moved over time, scattering material across the outer regions. This migration likely influenced the architecture of the Kuiper Belt, shaping resonant populations and contributing to the scattered disk. Similarly, understanding the Oort Cloud's population and structure provides clues about the early solar system's interactions with its stellar environment, revealing how external forces shape the distant boundaries of our cosmic neighborhood. Beyond their scientific significance, these distant regions captivate the imagination. They challenge our perception of the solar system's shading and complexity, extending its boundaries to nearly interstellar distances. They remind us that while planets dominate our mental map of the solar system, the majority of its mass may reside in smaller, icy bodies far beyond the reach of the naked eye. Each comet that emerges from the darkness of the Oort Cloud, or each Kuiper Belt object imaged by a spacecraft, is a messenger from the solar system's outermost edge, carrying secrets of formation, evolution, and the persistent forces that continue to shape our celestial environment. As we continue to explore and study these icy frontiers, new questions emerge. What is the true extent of the Oort Cloud, and how many objects does it contain? How do interactions between Kuiper Belt objects and Neptune continue to shape the region's structure? Could some Kuiper Belt bodies harbor subsurface oceans, driven by internal heat or radioactive decay? How common are similar belts and clouds around other stars? And what does that tell us about planetary system formation throughout the galaxy? Each discovery prompts new avenues of inquiry, revealing that the edges of the solar system are not a final boundary, but a gateway to endless scientific exploration. The Kuiper Belt and Oort Cloud also highlight the delicate balance of cosmic forces. While these regions are distant and seemingly isolated, their interactions influence planetary systems and even life-bearing worlds. Comets can deliver water and organics, collisions can alter trajectories, and gravitational resonances shape the architecture of the outer solar system. This interconnectedness emphasizes that no part of the solar system exists in isolation. Even the farthest icy bodies are tied to a complex web of forces that extend from the Sun to interstellar space. In considering the Kuiper Belt and Oort Cloud, one cannot help but appreciate the vastness and dynamism of the solar system. These icy regions are living archives of cosmic history, preserving the remnants of the formation process while continuing to interact with their surroundings. They are at once ancient and active, distant yet influential, simple in composition but complex in behavior. As humanity ventures further into space, both observationally and through spacecraft missions, we will continue to unlock their secrets, deepening our understanding of the solar system and our place within it. Looking beyond our own solar system, the study of the Kuiper Belt and Oort Cloud provides a window into the architecture of planetary systems throughout the galaxy. Astronomers observing young stars often detect debris disks, rings of dust and ice, that echo the structure of the Kuiper Belt. These disks suggest that the processes shaping our outer solar system, planetary migration, scattering of icy bodies, and the preservation of primordial material may be common throughout the universe. By comparing these distant systems with our own, scientists can explore whether the formation of icy belts and distant cometary clouds is a universal feature, or if our solar system's configuration is unique in some way. Such comparisons may even provide insight into the likelihood of life-bearing planets elsewhere, as the delivery of water and organic compounds via cometary impacts could be a widespread mechanism in shaping habitable worlds. The edges of the solar system also offer profound lessons in cosmic scale and perspective. While planets like Earth and Jupiter dominate our imagination, the vast majority of the solar system's volume is occupied by distant, icy regions that rarely interact directly with the inner planets. The Kuiper Belt, though relatively close in astronomical terms, lies billions of kilometers away, and the Oort Cloud stretches halfway to the nearest stars. These regions remind us that what we see in the night sky is only a fraction of what exists, and that the true solar system extends far beyond the planets we know and the moons we have studied. It is a realm where time moves slowly, distances are immense, and processes unfold over millions or even billions of years, offering a humbling perspective on the scale and persistence of cosmic forces. Scientific exploration of these regions continues to push the boundaries of what is possible. Telescopes such as the Hubble Space Telescope and the upcoming James Webb Space Telescope allow astronomers to detect faint Kuiper Belt objects, study their compositions, and track their orbits with unprecedented precision. Ground-based surveys, including those using wide-field imaging systems, continue to catalog new Kuiper Belt and scattered disk objects in missions, revealing the immense richness of these outer regions. Meanwhile, technological advances may one day enable spacecraft to venture even further, probing the scattered disk or indirectly observing Oort Cloud bodies, transforming our theoretical models into tangible knowledge. The Kuiper Belt and Oort Cloud also serve as reminders of the dynamic interplay between stability and chaos in the cosmos. The Kuiper Belt's resonant objects illustrate how gravitational relationships can create stability over billions of years, while scattered disk objects and Oort Cloud bodies demonstrate the vulnerability of distant orbits to perturbations. Long-period comets arriving from the Oort Cloud are a testament to this delicate balance, sometimes appearing suddenly and unpredictably, yet following physical laws that govern the motions of bodies across light years of space. These interactions provide a natural laboratory for understanding orbital dynamics, resonance effects, and the long-term evolution of planetary systems, bridging the gap between theoretical astrophysics and observational reality. The human fascination with these distant regions is not merely scientific, but deeply philosophical. The Kuiper Belt and Oort Cloud push the limits of exploration and imagination, challenging us to rethink what it means to define the solar system. They are reminders that boundaries are not always sharp, that our knowledge is always provisional, and that the universe holds far more than what we can immediately observe. Each comet, each distant dwarf planet, each icy fragment traveling through space tells a story of origins, migrations, and transformations that occurred long before humans gazed at the stars. By studying these regions, we connect with the deep history of the solar system, tracing a narrative that extends across billions of years and billions of kilometers. Moreover, these distant icy bodies may have played a critical role in shaping life on Earth. The delivery of water, organic molecules, and other essential compounds via comets from the Kuiper Belt and Oort Cloud could have created the conditions necessary for life to emerge. Understanding the composition and frequency of such impacts informs models of planetary habitability, not only for Earth but for exoplanets as well. The study of these outer regions thus intersects with astrobiology, cosmochemistry, and planetary science, making them central to our understanding of life in the cosmos. Future exploration promises to expand our knowledge even further. Missions designed to fly by or orbit Kuiper Belt objects could reveal the geology, internal structure, and chemical composition of these primordial bodies in exquisite detail. Innovative concepts such as sending swarms of small probes to the scattered disk or detecting Oort Cloud bodies through their thermal signatures could bring these distant regions into closer reach. Each new observation will refine our models of solar system formation, test hypotheses about planetary migration, and deepen our appreciation for the intricate and interconnected nature of celestial mechanics. In the end, the Kuiper Belt and Oort Cloud stand as twin sentinels at the outermost reaches of our solar system. One forms a broad, flat ring of icy relics just beyond Neptune, while the other envelops the system in a vast spherical cloud stretching toward the interstellar medium. Both preserve the history of the solar system, both contribute to its ongoing dynamism, and both challenge our understanding of distance, scale, and time. They remind us that the solar system is far more than the planets we see and the moons we visit. It is a sprawling, intricate system shaped by forces that act across incomprehensible distances and immense spans of time. As humanity continues its journey into space, the Kuiper Belt and Oort Cloud beckon as final frontiers within the solar system itself. They offer a wealth of scientific discovery, the promise of understanding our origins, and the enduring allure of the unknown. Each comet that streaks across the night sky, each faint Kuiper Belt object imaged by a telescope, and every theoretical model of the Oort Cloud structure deepens our connection to the cosmos, reminding us that even at the edge of our sun's influence, there is a universe of wonder waiting to be explored. The solar system's edge is not a boundary, but a threshold where history, science, and imagination converge, illuminating the enduring mystery and majesty of our place in the galaxy. In this way, the Kuiper Belt and Oort Cloud are far more than remote repositories of ice and rock. They are active participants in the solar system's ongoing story, chroniclers of its past, and harbingers of its future. Through them, we glimpse the processes that built planets, the forces that shaped celestial orbits, and the cosmic mechanisms that occasionally deliver life-giving material across vast distances. They are both a record of what has been and a promise of discoveries yet to come, embodying the profound interplay between distance, time, and the ever-unfolding dynamics of the cosmos. By studying them, humanity expands its reach, its knowledge, and its imagination, venturing ever closer to understanding the full scope of the solar system and the universe beyond.